All right, let's dive right in. We're going to talk about something that is literally all around you, but you probably never ever think about it, the world of non-woven fabrics. We're going to pull back the curtain on the incredible, high-tech machines that turn simple fibers into things we use every single day, from face masks to construction materials. So, let's get into it.
So chew on this for a minute. What if you could make a strong, durable, useful sheet of fabric without a loom, without knitting needles, without any of that complex weaving you see in traditional textiles? I mean, it sounds kind of like magic, right? But it's not. It's the core idea behind a massive global industry.
And this is what they're called, non-wovens. You can think of them as engineered fabrics. They're made by taking loose fibers and then tangling or bonding them together. And trust me, they are everywhere. The filter in your face mask? That's a non-woven. The wipe you use to clean your kitchen counter? Yep, a non-woven. Even the stuff that stabilizes the ground under our roads? You guessed it, non-wovens.
Okay, so what are these things, really? Well, unlike your cotton t-shirt or your denim jeans, these fabrics are engineered from the ground up, literally fiber by fiber, to do a very specific job.
You know, the easiest way to wrap your head around this is to think about the oldest non-woven fault time, felt. You just take a bunch of wool fibers, add a little bit of moisture and pressure, and they just tangle up. That very basic physical principle, that's exactly where the whole story of this machinery begins.
Right, so how do you take that super simple idea and turn it into an industrial process that can make miles of fabric? Well, you build a machine that can tangle fibers together with incredible speed and precision. So let's start at the beginning, with the first machines, the mechanical origins. Now, check out this timeline. You can see the innovation starts kinda slow in the late 1800s. But then, look what happens after World War II. It just explodes. Melt blowing, flash spinning from materials like Tyvek, hydroentanglement, all of these pop up in just about 15 years. This was a massive leap from simple mechanics to some seriously advanced polymer science.
So let's look at that very first mechanical process. It's called needle punching. It's basically brute force, but it's elegant brute force. First, you open up and mix your raw fibers. Then, a machine called a card gets them all aligned into this fluffy, super fragile web. You then layer that web back and forth with something called a cross-slapper to give it strength in all directions. And then comes the magic, the needle loom. We're talking thousands of barbed needles punching up and down like crazy, grabbing fibers, pulling them through the web, and tangling everything up into one solid piece of fabric.
But just punching fibers together? That was only the beginning. The mid-20th century brought this absolute revolution in plastics and polymers, and it completely changed the game. Engineers suddenly realized, hey, wait a minute, we could skip the fiber stage entirely and make fabrics directly from molten plastic. And this led to two amazing technologies, spunbond and meltblown. For spunbond, I want you to think of a high-tech pasta maker, pushing out these long, continuous filaments that give the fabric its strength. For meltblown, imagine taking that molten polymer and blasting it with hot air, creating this cloud of incredibly fine microfibers that are perfect for filtration. But here's the real stroke of genius. Combining them. When you layer them together, spunbond, meltblown, spunbond, or what we call SMS, you get the best of both worlds, strength and filtration. And that's the secret sauce in high-performance medical gowns and face masks.
And this quote just nails it. It perfectly captures the feeling of the time. I mean, think about it. The idea of creating a finished fabric directly from a tiny plastic pellet with no spinning, no weaving, that was a monumental leap. It must have felt less like a textile mill and more like something straight out of science fiction.
And the companies that mastered these processes back then are still the leaders today. You've got Reifenhauser-Reichafil, who keep perfecting spunbond technology, making fabrics lighter and stronger with every single new machine. Oerlikon are the masters of meltblown. They even figured out how to add an electric charge to the fibers to make them super efficient filters. And of course, there's DuPont, whose totally unique flash spinning process gave us the iconic Tyvek.
But hey, not all the innovation was about chemistry and heat. While some engineers were busy melting plastic, others were looking at a completely different set of tools, the fundamental forces of nature, like water and air.
And this idea is just brilliant. Forget needles, forget melting plastic. What if you just used incredibly fine, high-pressure jets of water to do all the work? You could blast a delicate web of fibers, and the sheer force of that water would tie them all into these intricate little knots, creating a soft, cloth-like fabric. This is called hydroentanglement, or you'll often hear it called spun lace.
And here is where it gets really cool. The machine builders Voith and Truchler combine two different technologies. So first, one machine uses water to create a sheet of natural wood pulp fibers. It's almost like making paper. Then, another machine immediately uses those high-pressure water jets to bond it all together. And the result? A completely plastic-free, biodegradable, flushable wipe. It's just a perfect example of how you can combine technologies to solve very modern problems.
And that brings us right up to today. The nonwovens industry isn't just about clever mechanics or chemistry anymore. No way. It's a massive, high-tech, data-driven global business, and it's all focused on performance and sustainability.
Just to give you a sense of the scale, we're talking nearly 3 million tons. Let that sink in. That's how much non-woven fabric is produced in Europe alone every single year. That is an enormous amount of material going into our hygiene products, our cars, construction, and healthcare.
And that growth is steady. You can see it here. In North America, the capacity to make these materials just keeps on climbing, year after year. And it's not surprising when you think about it, right? The demand for better hygiene products, lighter cars, and advanced medical fabrics, it's only going up.
The crucial thing to get is that today's factories are incredibly smart. They use these high-speed scanners that are like 1,000 quality inspectors, measuring the fabric in real time and making automatic adjustments on the fly. The goal is ultimate efficiency. You hear terms like down gauging, which is just a fancy way of saying using less material to get the same or even better performance. Other systems make sure that even at mind-boggling speeds, that initial web of fibers is absolutely perfect. It's all about control, and it's all about precision.
So, when we look ahead, it really all boils down to three big things. First, sustainability. We're seeing more and more demand for materials like those biodegradable wipes that can actually return to nature. Second, efficiency. Making fabrics that are lighter, using less energy, which is obviously good for the planet and for the bottom line. And third, high-performance filtration. Because let's face it, the need to clean our air and our water is only getting more critical.
So, think about it. We've gone from simply tangling wool fibers together by hand to creating these incredibly smart materials that can filter microscopic particles and literally protect our health. These invisible fabrics are already shaping our world in ways we don't even see. And the real question is, with this incredible technology constantly evolving, what seemingly impossible problems are they going to solve for us next?